Hello, hello, and a very good evening. So, I thought I would try something very, very new on this channel today. Something that I have never done before. Usually, I've only put gaming things on this channel. But trying to learn a new programming language, or new, it's not really that new, but it's new to me, and I'm trying to learn Rust. And I think many people probably associate Rust with the game, and perhaps some people that drop into this channel that know me would expect this to be about the rest of the game, but no, this is about programming. So I do sincerely enjoy programming. It's something that I've been doing since I was 11 years old when my father bought me a compiler many, many years ago. And he bought me what is called MetaWorks Code Warrior, and it was a C programming environment for Mac OS. And I think the first time I saw it, I didn't know quite what to do with it, but I sort of fiddled with the code that came with the compiler as examples. And this sort of got me thinking about how programming worked, and it turned out to be sort of intuitive for me, at least over time. And before long, I was writing very, very simple Macintosh games. And this is many, many years ago. We're talking pre-Mac OS X here, preceding Mac OS X by many years. So it was Mac OS like 7 or 8, which were good times back then. So one interesting sort of thing that has been like a journey for me when I think about it is that I started out with C programming. That was the first language that I ever touched, and then I learned C++, which was also very cool, and I remember really enjoying C++. Looking back at it, I think there was a lot of boilerplate code with the headers and the classes and everything. But gradually, then I think the next language I learned was Perl, actually, because I installed Linux and Perl was like a thing, and sort of scratched the surface on Python. And over the years, that also became a language that I've used quite extensively. And then one thing that happened was that I got into C sharp. I never really liked Java, but C sharp really clicked for me, and it became the language that I went for many, many years. And I used it professionally, and it was the first language where I made software that ended up in systems that are still running today, even though it's I think 16 years since I wrote my first C sharp program, and some of those things are still operating today, and that is cool. But now comes Rust, and Rust, in some ways, reminds me a little bit about about C in the sense that it's not a it's not it's not a managed language in the same way that C sharp is. You can the thing about Rust is that it is not garbage collected, so you have to manage your own memory the same way you did have to do in C and C++. But at the same time as it allows you to mess with memory and allows you to get rid of all these frameworks that are or this infrastructure that you need to have software that is garbage collected run, well, it gets rid of those things, and then it has to manage memory, but to make sure that you do it correctly, it puts very strict rules on how you do it. And this adds a lot of complexity and sort of mental overhead to using the language. And it adds a layer of sort of, I think I looked into Rust a while ago too, and the first thing I tried to implement was a graph structure that I was using in a piece of software I had already written in Go. And I had also written it in TypeScript to test. So in both those languages, the same sort of structure worked really well. It's a graph structure basically, and each node had a reference to the graph that contained that node. So it was easy to make an API that allowed you to manipulate the graph on the nodes. And this was the first thing that I tried to implement in Rust, and completely failed. It just utterly. It was such a horrible experience, and eventually I didn't manage to do it because of the way that it manages memory. It's not so easy to make these cyclic structures that contains references to itself in any way, or yeah, basically that's it. It's structures that reference itself is really, really hard in Rust. It's not to say that it cannot be done. And graph structures certainly exist. And the same with linked lists. And in fact, one of the ways you can learn about memory management in Rust and Rust in general is a book where they implement linked lists. And that's the only thing that they do in that book. It's just that. So these are probably poor beginner structures in Rust. And I've gotten a little bit further now on my second attempt. And it is alluring, this language. And the reason the thing that really hooks you and takes you in is the fact that it creates tiny, super fast executables that requires no infrastructure to run. So for our upcoming project, I'm really interested in using WebAssembly and also to use form function interfaces on other platforms. And looking at these things, I'm thinking that this language is absolutely fantastic if it allows you, even though there's a strong learning curve to the memory management of this language, that it then allows you to create tiny executables that can run in browsers with WebAssembly and on servers and embedded in microcontrollers if you want. This span of things you can do with the software. It's pretty fantastic. And if it then prevents things like race conditions because of these restrictions or these sort of limits that it puts on memory, then these are really interesting things for my upcoming project. And because of that, I wanted to learn a little bit more. But I think in this time around, and I haven't gotten that far, I have to say, but this time around, I want to learn the language more, starting with simpler structures or structures that are not so challenging to implement in Rust. So today I thought I would just, this might be a more than one stream like I've written on the slide here. But what I wanted to do is I wanted to experiment with sharing data between threads that are executing and just seeing how that goes. And then I want to use the knowledge from that to implement an epidemiological model that basically simulates the population of individuals that infect each other. You see all these sort of sigmoid curves where you see a rapid exponential increase and then it tapers off and eventually flattens as immunity builds up in your population. It would be cool to, I have written these kind of models before, just in other languages for fun, and I think writing a very, very simple one in Rust is interesting. I have tried some of these things and they seem to work. So I'm going to make another attempt now and try to make a stream of it. And if someone is interested in this and wants to follow along, please do comment in the chat, or yeah, you can add your opinions about my code. I'm not a very good programmer, so there is no promise here that this will be like a tutorial on how to do things, but perhaps it's an interesting thing to scroll to for people in the future if they are facing the same kind of questions. One final comment about Rust before we get going is that I think the language is beautiful. And it sort of comes down to this very, very simple data structure and generics system that it has. The first is the enums containing data. It's just so crazy cool, and just that concept alone makes this language intriguing, and that itself is a strong hook. The excellent generics that I've seen so far really, really also makes it look amazing, and that is like the thing that I miss in Go when I program Go, and I just tried that to test it out. By the way, Go produces incredibly. It can compile to WebAssembly, but it creates huge executables because of that infrastructure that it needs to operate the language with the garbage collection and so on. And because of that, I think that I'm going to put Go aside and focus a bit on Rust now. But these aspects of the language is that also the structs basically as the core sort of data type instead of classes. The traits, it's like this language seems so well designed, but of course it has a lot of drawbacks too, because this management memory management starts to look really messy. Although I think you can also sort of put some lipstick on that and make your code look reasonable. So I'm not really comparing Rust and Go, by the way. I think these languages are quite different. This apples and oranges thing that people often mention. So they are quite different. Okay, I'm just going to save this in case these slides in case I need them for the future. Okay, so for the IDE today, I am going to use CLion, and I will show you why in a moment. I think Sea Lion is pretty cool. It's from JetBrains, and they are like consistently delivering fantastic experiences or IDEs for me anyway. In other languages, I've used WebStorm, and I've used Golang for Go, and I've used WebStorm as well for TypeScript. These things are really nice in my experience. Okay, but let's get going. So the first thing I want to do in the stream, like I said in the introduction, was I want to try to share memory between threads. And if you're going to write an epidemiological model, you're going to simulate as large a population as possible, I guess. Or maybe it comes to like a limit where you don't need to simulate more people in your population. But having a very fast execution of that model, so you can simulate, let's say, 600 days of epidemic in 5 million people would be an interesting goal, and having the ability to do that within a reasonable amount of time would be cool. So I think in order to achieve that, we need multi-threading. And one of these concepts in Rust that are difficult is exactly how do you share resources. So Rust has this concept of fearless concurrency, that if you do abide by these rules that it provides, then you don't have to worry about things in multi-threaded execution that you have to worry about in other languages, such as data races. And because basically a thread has to own its own data, so there will be limits to how much you can fuck up or mess up this sort of interaction between the threads. Okay, so let's get to it. We're going to create first a little toy project to check out this memory management and sharing resources between threads. Because I know that if I want to execute this epidemiological model really well, then I have to have threads to process as you simulate, and those threads have to share resources. So they have to read and write from resources that are shared between them, because any patient or any individual in the simulation can interact with any others. So you cannot isolate the data that you push into the threads. Or could you? Perhaps you could design an architecture that could do that. But yeah, anyway, let's try to do this with threading and then see how it goes. And there are no guarantees that I will succeed at any of the things I'm going to do today, but I think it's worth a test. Okay, so in Rust, the first thing you do is when you start a new project is that you will use the built-in system called Cargo to create a project. So we will do that. This font probably comes up a bit too small in the stream. Let me change that. Let's see, profiles, and we will put the text. Where is that? Custom font. Looks good. Let's put that up to bigger size. It's rare that I find a monospaced font that I like. Actually, JetBrains also makes a great one called I forget it, but JetBrains actually made one for their integrated development environments that makes it easier to read code. And I thought that was kind of neat of them to do what's called JetBrains Mono. Yeah, anyway, it's a good one. But let's keep at it with this. So I'm in project here. I made a little hello world just to see that my IDE worked. So I'm going to use Cargo. And Cargo, if you don't know, is the package manager, and sort of it's just a general tool for Rust code to create projects and manage crates, which are packages that you produce in. There's a build system and package manager for Rust. So let's do cargo new. And we're going to call it shared thread data. So it has created that. So let's get cells into Sea Lion. This is the Rust page, by the way. I guess we don't need that now, but I have a feeling there'll be a lot of Googling in this stream. Okay, so let's open this new project, and I think Sea Lion will create for us a IDE settings directory and so on immediately in there. Let's have a look and see if we go to shared. Yes, now it has created a little directory for itself. So just opening the project folder creates an IDE. It's like set up with project data and so on in that folder. Okay, so let's have a look. So this is our first file. Let's make it a bit bigger. Let's just see that it runs. Hello world looks good. And since we are using a wide format, let's put the window over here maybe, so we can look at the output and all the red text, all the bugs and all the crap that's going to put out there eventually. Okay, so this first example, what we're going to do is we're going to create a let's create a list. Let's create a list of items, and then we will have the threads we have multiple threads add data to that list, so that the order of the data will be irrelevant, but we want them to not, we want to be able to do that kind of thing in Rust, even though it is highly managed, the memory of this system. Okay, so let's first create our list. So we're gonna create a list, and it will be a vector of strings. So look at this beautiful autocomplete thing here. I love this. Now it doesn't know. It knows that it's a vector, but it doesn't know what kind of vector. Actually, we can just leave it like that. Will that compile? I'm not sure. Let's try and build that. No, that will not compile. So it has no type information here, so that's undeclared yet. So let's add some strings to it. Actually, we'll do this. We're gonna do, of course, we're gonna do hello, and then we're gonna do this to string as. So Rust has this intricacy where it has two string types. One is sort of hard-coded and stays on, and as far as I understand, it gets instanced on the heap. No, on the stack. But if you do the string with the capital S instead of this str, which is the stack one, then you get the string allocated to the heap, and the string will become mutable. So I'm not actually sure which one we need here. Maybe let's try just use this. And if I do this, this should now be a string. Yeah, so it's now a string pointer. Let's try this. Actually, this could break. But let's try that. Okay, so the last thing we're going to do is we're going to print the output of this. So we're going to do the print line macro, and that will have, actually what we're going to do is we're going to do result, and then we will join the list. So we'll do join with a separator, and the separator is going to be a comma, like that. And if you run this program, we should now be able to see hello world, and we did with a comma separated. Yeah, so that works. So two things, if anyone watching is not aware of how Rust works, or the syntax of the language. So this is a macro. This is not actually this is a convenience macro to instance this vector. We could implement it differently. Let's do let list equals, and then we do vec, which is the struct or the type, and then we're going to create a from. We can use from, and yeah. So what do you create it from? So actually, I think we have to declare what it is, or do we? So the vector we are getting is a vector with a generic type string, like that. So I think let's see if we can add more than one. So we can do vec from. Can we add multiple things here? Hello. Will that work? Let's just try this. No, it doesn't work with it. Doesn't have a size none that compile. Oh, interesting. Actually, that one I don't actually know. Yeah, so it's very particular about this actually, because it has to know, for a lot of these data types, it has to know how big they are when it can allocate them. So why this doesn't work, I'm not sure. Maybe it's because it's a vector of strings. So maybe a vector of string pointers is easier. Let's try that. Expected. And then here, maybe can we do this? No, we can't do that. Trait. Why can't we do this? Okay, so it cannot do that like that. Yeah. Okay, but then we stick to the thing that we know works. We can create a vector of string with a capital S object, which is on the heap. And I guess this will now contain only pointers. So let's say we created a new vector like this. Now it's empty, there's nothing in it. And then we could push onto this any value we want. But okay, so if I actually just write a string here now, I don't think this is going to work because it's not the same type. Yeah, so now it says Expect a string, but found a string pointer. Yeah, interesting. What you can do is you can take the string and you can make it to string, fascinatingly enough, and then it converts this into a string on the heap. Okay, so here we have another error that says cannot borrow immutable local variable list as mutable. Oh, that's a fascinating little Rust thing, right? So if you're looking at this and you come to the language, you're going to be, what the fuck does that mean? Like, what does that mean, that message? Let's try and compile and see if it gives a suggestion. Okay, so the problem is cannot borrow as mutable. So cannot borrow list as mutable as it is not declared as mutable. Mutable in Rust, as far as I understand, means that you can both read and write. So if you want a variable that can be mutated, like this vector, so right now we're saying that this vector is static; it cannot be changed. Nothing can be added to it. So what happens is when you implement, as far as I understand, and this is again based on my limited understanding of this language, when you implement methods on this vector, or the associated functions for this vector, then you have to specify whether the method takes a mutable or an unmutable version of the object that it modifies or that it applies to. So the self or this object becomes either mutable or unmutable. So what we're trying to do here when we're doing push is that it requires a mutable self. If you look in this declaration here, it says this is on the third line there, I can't move the pointer there, but it says public function push, and it requires a mutable version of self and a value to push onto it, and that value is of t, which is a generic for push anything into this vector. So the solution to this is simply to declare it as mutable. But when you declare something as mutable, that put other limitations on that object or that variable. So now it should run. Okay, so this worked, but it's much easier. I'm just going to try one more thing. Let's say that we actually had this as we wanted it to be a string pointer vector, and then we saw that when we declare a string just like this, yeah, maybe let's see this if this works. And that also worked, yeah. So we could do that. But what I'm curious about is when we do this, what happens if we take this vector with these variables that, as far as I understand, are bound to the stack and not to the heap? Then can this ever leave? If this function, when this function ends, when we fall off the end of this declaration, does this stay in memory, or is that stack frame cleared? And I have a feeling this would not work well, but we can start with it and see how it works. Actually, let's do that because I think this is the better declaration to use the heap declare strings, but it will be an interesting experience to try to do something else. Okay, so the next thing we want to do is now we want to make a multitude of threads that mutate this list. That we've already shown that within this particular function we can mutate this list and we can add things to it. But what happens if multiple threads want to do it? So one more interesting thing here. Since this is the first stream, I'm just going to give this example. So I'm going to make a function here that says takes a thing, and this takes a thing. It takes a vector of string pointers. But we're going to call that taken. And then what it does is that it prints the length of this. So it will do, let's say, we're going to take the taken.len, I think. Yep, there we go. Okay, so that's what this thing does. Let's comment out this final thing. And then we do that. We use the function that we declared. We takes a thing and we give it list. And here, if you haven't programmed Rust before, you might be in for a shock in a moment. Yep, so it prints the correct length. So it is long, this item. Okay, so let's run that again. It says it is one item long, or taken thing. Taken thing is one item long. Okay, so we know that this works, right? So here's an interesting thing. We would perhaps want now to then print the results here. And now we're going to get a problem because if I run this, it says value borrowed here after move. This is also one of those things, if you haven't read up on Rust before you start programming this, you're going to be, what the fuck does that mean? Because it's so alien if you're sort of unaware of this type of programming style, I guess, and it is just sort of, it blows your mind that this could be a problem. So this is the infamous borrow checker, and what it means is that if you give if you give a variable to a function, the function takes that variable. It goes out of scope in main. So I've literally given it to this function, and this function doesn't return it. So when you come to the end of the takes a thing function, when this function fall off the edge, then it's gone. Just like that. Then this thing doesn't exist anymore. So this is how Rust manages memory without a garbage collector. It means that when an item is no longer going to be used in the future, it removes it there and then. So it statically analyzes this at compile time. So this is a different. This is a very, very different way to manage memory, and it's quite fascinating, right? So the answer to this, if you wanted to do this, would be properly would be that you would instead give it a reference to this vector. We can try that now. So now we're saying that we are borrowing this vector. The taken is now a borrowed vector. Essentially what we're doing here is we're giving it a pointer. It may or may not work. Yeah, so that worked. And now borrowing means that instead of dropping that element from memory when it's done, it sort of gives it back, or it doesn't give it back. It's just the borrowed reference goes away. But Rust's mysterious borrow checker basically says that there are limits and there are rules to what you can borrow. And borrowing out a mutable vector is not so easy. Let's say that we wanted takes a thing to mutate this vector. I think we cannot do this. Let's try this. So we have a mutable vector, and now we're borrowing it as a mutable vector to another thing. Can we borrow a muted? Actually, we could. Okay, so my examples are messing up here. Okay, so there are limitations. Let's see. What I do know is I cannot borrow a borrowed vector as a mutated vector. Let's try one more time. I'm just gonna make one more. It takes it again, and then we're gonna do the same thing. Actually, we're gonna just copy this thing so this function does exactly the same thing. Let's see if we can implement this. So let's say that this one, does it matter if we then do takes it again? Maybe not. Takes it again. Let's try this. Maybe it doesn't matter. No, so that doesn't matter. Okay, so this is interesting, and this is also part of the learning for me again. Remember, this stream's point is to help me learn as well. Can I borrow it? Let's say that this only requires a borrowed vector. Can we do that? Yeah, so that also worked. But yeah, okay, so now we know that you can pass a you can borrow a mutated vector forward in this way, and that works. And we also saw up here that this mutable variable could also be borrowed as a non-mutable variable. So if I did this again and I removed the mutable, then see this? Yeah, so that also works. You can take a mutable vector and borrow it as an unmutable, but you cannot take an unmutable vector and borrow that, I think, if we borrow that as mutable. Let's try that. So we now say that this one takes a mutable, and then no, that doesn't work. So you cannot take a borrowed. Okay, so you cannot take a borrowed value and mutate it. So once you have given read access to something, the reader cannot change that variable. So my headset lost power here for a bit. I hope I still have sound. Yeah, it seems like I do. Okay, so let's continue this silly adventure. Let's do our little thing here. So what we are again trying to achieve is we want to mutate this vector that we have here now across multiple threads. And that's again with the goal that we want to make an epidemiology model that will require multiple threads to process the simulation and share data between multiple threads. Okay, so let's remove this, and again the goal is just to mutate this. Actually, we can just keep this because the code is simpler. So we're gonna define a vector or define a list of words, And now we're gonna spawn some threads. So spawning a thread in Rust is super simple. You literally just use spawn. And spawn is in the threading namespace. This is how that works. So we're gonna spawn, and then we have to give it an enclosure or an anonymous function that will do something. So we can just actually we can just spawn a thread that says hello from thread. Let's see if this runs. I think it will spawn the function, but it might be that it cannot print because it's going to run off this thread might be behind the main thread, and then it will execute. It will complete the program before it can run. Let's see this. That worked. Let's try it a couple of times. If we're fortunate, we will have some kind of heavy crash. No, it work. Okay, so when you spawn something, you get a thread handle so that you can use to synchronize and join afterwards. So we're gonna this is called a join handle. So we're gonna create a variable called join handle like that, and then since we want to spawn multiple threads, we're gonna create a vector again. So we're gonna have a list of handles, or yeah, we're gonna call it handles, and that will be a vec. And I gotta show you this beautiful type. Well, it figures out these types beautifully, and in CLion you will see these unfinished types as they're going, and it's really cool. So right now I have a vector here, but I haven't said what type it is, right? It's just a vector, but Rust is absolutely strongly typed. So right now this is not going to go, right? Because it needs to know what is the inner type of this generic vector. So what are we going to do now is we're going to add this join handle here to handles, and look up here what happens when we do that. So we now, to handles, we push the join handle. And just look at that. It just figured that out, that now this is a vector of join handle. So you don't need to, this is kind of nice because you don't need to be very verbose about what you declare. I like that about Rust so far. It's something that I really appreciate. It reminds me of going from C# before the var variable type, because then that was before C# inferred variable types. And here you really see how well it infers it. Okay, so we have a problem here. It cannot borrow immutable local variable handles as mutable. Again, the same problem as we had up here. So we all both want list to be a mutable vector, and we want handles to be a mutable vector. Now we're just spawning a single thread. We can just try this. Actually, the reason we're putting it into handles is, of course, because we want to synchronize as the last thing we do. We want all the threads to have performed their work before we print the contents of the vector. So we want to sync or wait for threads to finish. So we're going to do for handle and handles. This is also a very, very, very pretty syntax. Note that this is an inferred thing, so if you actually didn't have this auto-completion, or this, no, not auto-completion, but this sort of augmentation that CLion provides, then you wouldn't have to see this. Actually, let's open this one. We can take a little peek at that. Let's see, show in files, and then we can see, if I now open this in text editor, you'll see that the code looks much cleaner if you don't have this like here it says, handle, and then there is this type declaration here. That's not in the actual text file. If you were just writing it without these augmentation things that are very useful, especially when you're learning the language, then the code looks fairly clean in Rust. I don't think it's an ugly or unclear language. I think it's pretty neat for most things, but it does go off the rails every now and then. We're going to have an example of that shortly, I believe. Okay, so each of these handles we will now join, which means that it stops there until that thread has completed execution. So the code will stop here until, the code will stay in this loop. It will not cycle, but it will stop on these joins until all of them are done. And then we get here and we can print out the results. So this is a synchronization point. Okay, so let's look at this. Let's run it again, see that it compiles, and we are getting variable does not need to be mutable. Okay, that is true because a result and used result that handle join. Right. So We can do two of these things. So yes, indeed, the list does not have to be mutable, but that is because we are not adding anything to it, but we will shortly. The next thing here is maybe more interesting. It is that there's an unused result that must be used. And it happens on this line here. So let's have a look at the result type in Rust. Rust result. This is also something that's kind of neat. So you can see that when you perform some action in Rust, you very often you get this type called OK or error, and this is one of those beautiful sort of data containing enums that I was talking about earlier. That the various elements of an enum can contain different types of data. So in this case, it has an error type. This result has an error type of a specific type E, and it has a data type of type T. So what it means when you have a result come out of a function, it means that this can either succeed or fail, and then you need to handle the error. I don't think we're going to handle the error here, but you can use a match expression. So you can do match, handle join, like this. Then it's going to say something like, yeah, there you go. Okay, so this is, that was a beautiful code completion thing there from CLion, by the way. So now you can see that it takes, depending on whether you get OK or an error, you can do one thing or the other. The other thing, so this is how the error handling works in Rust, and it also uses this for something called an option, which is instead a function that may or may not return anything. But if it doesn't return anything, it returns a none. But if it does return something, it returns that data type. So it will either return none or some. And if it returns none, then it doesn't mean that the function failed, right? It might simply mean that there is nothing there, like get this record from the database and maybe it's null, right? But nulls don't exist in Rust, so it has to be something similar to this thing called result, which is option. And then here as well, this result means did this succeed or fail. So if you wanted to do error handling in Rust, you can do this. But there is a shortcut, and that is unwrap. And unwrap basically you can do expect, I think, isn't that it? So if it crashes here, you will, let's see, or am I, yeah, I think that's it. So if I just do this, it means that it will crash it will panic or crash with this error. These runtime crashes are called panics in Rust. It will panic with this message, and the message is could not join thread. I actually don't know when you couldn't join the thread. Does it mean perhaps that the thread panicked? I don't know. Let's try and run it now. Unused import. Yeah, I think I imported this by accident by CLion, and because CLion, if you write something, it will import it automatically. Okay, so we still have this variable does not need to be mutable, but you can see here that this works. Okay, so what we actually wanted to do is, of course, up in this point here. We don't only, so we are now inside the thread, and we want, yeah, actually we want to spawn 10 of these, right? So I'm going to do for, and we're going to call n, or is it I? It's I, right? That's always what you use. So we want to do 10 iterations of I, and then we want to, okay, so for every iteration of this loop, we spawn a thread, and it writes this. Actually, what we can do is we can do, yeah, let's try this first. This is an interesting Rust thing here as well. Try to add in here. Yeah, so I wrote the wrong thing here. Indeed, it is I in this. Okay, so now it should run. Now we have 10 threads that write this, and they then synchronize, and we get the result thing here. So this synchronizes, this prints those things. This waits until all this is printed, and then it comes down here, and it outputs the list. It is the same list as we have up here. So for now, let's take this mutable away and just run the program again. Unused variable I. Yep. If you have an unused variable, you can do this, which means we're not going to use it, and there you go, no errors. But we do want to use this variable, and I'm just gonna. This is an interesting thing. It's not going to do so much for us yet, but it will shortly. We're going to add the I in here. This should work, right? You're spawning a new thread. You're taking the number of threads. So this is thread number number 1, 2, 3. So in principle, you should get 1, 2, 3, 4, 5 all the way to 10, or to 9. You get 0 to 9. But you might get it in any order because we are now talking parallelism, right? So these threads could execute in any order that you want, or at any random order. So interesting thing next then is, does this compile and run? No, it doesn't, because it says, and this is one of those Rust, very, very Rust specific things, right? Here it says, this may outlive borrowed value I. So, okay, one more crazy Rust type error, right? What does it mean that something might outlive something borrowed? Yeah, okay, so what's the principle? So inside this loop, we take this variable I, and we are generating this variable for each iteration of the loop. So we're generating 10 i's. So this problem with the I here is that once it comes to the end of the loop, it drops off the edge and the I is dropped. It's removed from memory. So it would mean that if you could do this, it could be that, and we are generating these on the stack. It means that once you are complete, once you run this thread, the loop here could have completed, because now you're executing in parallel in two different timelines. So what happens if you're done with your loop and you have removed the I and then you execute this print line statement? Probably the loop is faster than the thread spawning and this print line statement. So I'm pretty sure that by the time it comes to this, the loop will have completed. So that's exactly what this means. It means that that the thing that is created inside here could potentially outlive I, and it would. So the way Rust handles this, and I think this is neat, is that I can now say move in front of the thread, and then it moves into the closure. That's into this anonymous function that gets executed on the thread. It moves the variables inside of it, so it takes with it the I. It means that I can no longer think after here use the I because I've moved it into the closure. Let's try it now. And there you go. Again, you can see, yes, indeed, they are executing on different timelines, so the program is no longer sequential, it is parallel. Yeah, so that does work. Now the question again, once I have conducted a move, I can probably not use the I. So if I try to print the I here, print line, and we just simply print the I. It's probably now going to say use of moved value. Oh, that actually worked, didn't it? Fascinating. How is that possible? That is a mystery to me. I was pretty sure that I had figured this one out, but maybe I haven't. How would that work? Because now I moved this in. Does it mean that it moves it at the end of this? Gotta look this one up. Okay, so we're looking for Rust spawn. See if we have a simple explanation here. Waiting in thread. Waiting for all threads to finish using join. Using move closures. The move closure is often used alongside thread spawn. Allows you to data from one thread in another thread. You can use the move keyword before the parameter list to a closure to force the closure to make ownership of the value. Take ownership of the values it uses in the environment. This technique is especially useful when creating threads. Yeah, and it is true. We are not use. So it is very curious that it was possible to do that, even after we moved into it. Does it mean that it simply this now has ownership, but it's still available outside of the thread? Um, hmm, I actually don't know. Also a binding. I don't know if that's different from the other things, but this is okay. So this is a mystery for me. So that's the first question that I don't know yet. Why would this variable still be available outside the closure? Yeah. Okay. We will leave that mystery there. So we know that this works. So the next point then becomes, like we said before, we need to mutate this list. So let's assume now that we just tried that. Let's do list.push, and then we will format. There you go. So we'll just format a string that says porting from, and then this, the number there, which is the I. Yep. We're already getting an error message here. Uh, yeah, so okay, right. So mismatch. So in order to do format, we do have to use string with a capital S, as we said earlier, like a long time ago now. So we will change this for this vector, and now that error is we can do here. Then the question now becomes, yeah, so why does this not work? And the answer is, of course, cannot borrow immutable variable list as mutable. Yep, so that's the first thing. The list is mutable. This is not mutable. So we change it to mutable. Okay, so that error is gone. We can now push new things to the list, but it should not compile. And the reason for that is that we're now moving list into closure. Value moved into closure here in previous iteration of the loop. Right. So what this means is that because it's inside the loop, we on the first thread, first spin of the loop, we move list into the loop, into the thread, into the closure. But then, as I was expecting with the the iterator earlier, then it is no longer available because on the next loop you cannot move it into the closure again because it has already been moved. The first thread spawn now has ownership of that. You cannot multiple times move the same value in. Okay, just gonna go get myself a glass of water and then we will figure out how to sort this. So just one moment. Okay, so here we are again. So let's try to fix this problem now of the value getting moved into the closure. So what we need to do, okay, so we need to think about what we are trying to do. So someone is talking in the chat, and if you can speak English, that's better because I don't understand what you are trying to say. Sorry. Okay, so anyway, we are trying to resolve this problem where this vector has to go into the thread, and the vector has to go into the thread into all the threads. So we need to borrow to the thread a reference, but that reference also has to be mutable. So we need to be able to push a string onto that vector inside of these threads. So how do we do that? Well, there are multiple mechanisms to push objects. This took me a while to figure out. Let's try and open Chrome, and then we'll look at something called Arc, Rust. So if you need to have, so at this point in time, as far as I understand, the Rust compiler cannot really completely analyze this situation or this scenario. It will no longer completely understand how you will be using this list. Because of this, you need to think a little bit, you need to provide a mechanism that will keep the memory intact and safe at runtime rather than at compile time for these specific scenarios. So let's say that instead we had a list that we needed to process. Then you could, where you had no need to write it, then you could share just the reference to the list to all of them, or you could take it into chunks. And then if you were going to throw away the data you were processing afterwards, you could divide your vector into chunks, process the data separately in various threads, and then you would eventually just return the results and somehow aggregate the results from all threads. So what we're looking at here, however, is that we want to share a mutable reference that multiple things can do. So the first thing we want to do is we want to prevent multiple threads from editing the data at the same time, producing a race condition. So for that, we are going to need what's called a RV lock, read-write lock, and that is a cool structure in Rust. So the structure is called RV lock. What it does is it's like a mutex, a mutually exclusive. So what the mutex does, of course, is that it has some data inside of it, and then it limits your ability to read and write for more than one actor to read and write to that data at the same time. If you want to change that data, you ask the mutex for the lock, and you stop there until the lock is available and given to you. When you get the lock, then unlock it and you edit the data, and then it gets locked again and awaits the next actor that wants that data available. So the RV lock does the same thing, but it allows multiple reads at the same time. So if you're going to read the data, it does not require you to lock it. But all the readers have to complete before you can write. So RW or RV lock is cool. It's what we want basically. Or you could also use a mutex here, but I think RV lock is a cooler construct, so we're going to use that. So how would this practically work? It means that we're now going to put this list inside an RV lock, and then inside that RV lock, we will pass that RV lock into threads, so that multiple threads can use that RV lock. But the RV lock is no different from the vector in the sense that you can only give it to one thread. So this is one of those complex things that took me a while to understand, and one of the things that derailed me on my first attempt. It's the idea that you need to combine, in this particular case, you need to combine RV lock with another type. So let's have a look at it again. So we have RV lock, but there's also, so we need a way. Okay, so the RV lock allows you to mutate the data inside of it. That's what we're going to do. We're going to put list there, and then we're going to mutate the list, but we're going to do it in a way that ensures that there is no race conditions. And the way RVLOG does this is that it checks it at runtime. So now we are bypassing the compiler requirements by saying that this object, this structure, has a guarantee that this is going to be safe. But again, we can only pass it into one thread at a time, so we are back where we started. This does not work unless we find a way to share the RVLOC with multiple threads. The problem is that the compiler has no idea how many threads we're talking about. So it cannot check that at compile time. So in order to do that, what we will do instead is that we will create something called a reference counter. And what the reference counter does is that, let's say that I have a number. I put a number into a reference counter and then I give it to 10 threads. And I give it to 10 threads. For each of those threads, I clone the reference counter and then the reference count goes up by 1. Or if I had 10 threads, then the reference count is 10. And then what it does is that as all those clones get dropped as the threads despawn and finish their work, then the reference count goes down. So every time it drops one of the clones, it goes back to zero, eventually to 0. And when it's 0, Rust knows that it can erase the data from the heap. So the reference counter is a very, very simple memory management structure, but that is what we want here. So the counter provides also a type of memory safety guarantee. It provides that the data is not lost from memory before all its users have finished it. What we want to do is we want to put the RV lock inside the reference counter. And if we want to do asynchronous reference counting, so we want to access the reference count from multiple threads, then we use what's called a Rust arc. So arc is a thread-safe reference counting pointer, and that's what we are going for. So the only difference between arc and one thing called the other one is reference count, which is quite simply that. But right now we are using threads, so we need this is simply RC but with asynchronous arc. So we're going to use that one. We're going to put the RV lock inside, and then we are going to share the arc with the RV lock inside between the threads. Okay, so we have constructed ourselves now a small memory management system, right? So what is this memory management system? Well, we have now created a runtime memory management system for this list. We need to guarantee that only one thread at a time can change the list. We need to guarantee that the list does not go out of memory until all the users are complete. By combining rwlock and arc, we are now creating a very specific system of guarantees that will safely see us to the end with this, and then we can allow ourselves to do these things with these references, even though Rust's borrow checker would not allow us to move this type into it. So we are now moving the complexity onto the runtime, and these objects that we're working with now can panic if things go wrong at runtime. So what we're going to do is we're going to wrap the list, like I said, inside these structures. So we're going to do create shareable safe memory structure. Okay, so let's create the RV lock. So the RVL RVL, I'm going to call it read write lock equals RW lock. And notice that now, as I just tab completed this, then CLI and automatically that one. Okay. So let's do RV lock, and then what we want to do is, we want to create from, or I think it's new. Then what we're actually going to do now is we're going to move the list into the RV lock. So what we did now is that we took this operation. Notice that we're not borrowing it. We could borrow it, but we're not. We are not borrowing it, we're moving it. Sorry, my headphones occasionally drop out. Like I was trying to say, we are moving the data into the RV lock. Cool, let's keep going. We will now actually have a look at this structure because it's cool. Because now we have the RV lock, and how do we get the data out? Well, we ask to write or read. Let's see if we get a lock result. Let's say that we now want to read the list. I will ask for read, then I will unwrap, And then we can do push join, and we have all these things that exist on the inner value. They come out. What we've done with this sort of horrible construction is that we are now we are now taking back out with the read, and we can do this multiple times. So if you want to write, do write, then we would unwrap that or handle the errors. It might be that we stuck there. As far as I understand, if I do this, it waits for the opportunity for the write to become available. So let's say that I had 3 threads that were reading from the data, then those threads would have to complete their reads and have the read locks go out of scope, or this one could continue with the write. And that's how it synchronizes and keeps it safe. Okay, so let's continue this. Again, we said we need to share this RV lock, but it has the same problem as the list. If we move RV lock into this particular thread, then we have no then we have moved it and we cannot use it again the next time. So we need the ability to clone this. Like I said, we need a reference counter with multiple copies of the reference, and then have internally a memory safety that says when everyone is finished with this, we can go out of scope. Notice though that if you have a reference counter, an RC or an ARC structure like we're talking about now, yes, it does keep your memory safe, but it only does that on one sort of premise. And that premise is that you can no longer mutate that data. So if you put something into a reference counter, you can no longer edit it. So this has, of course, a lot of complexity, but because the RV lock can mutate the data, we can then share the RV lock, and that is why this is going to work. So we couldn't just put the list inside the arc, because only the arc only takes unmutable variables. So now we're going to take the RV lock and we're going to put it inside the. Actually, does it have to be? Yeah, it does, doesn't it? Otherwise, it cannot. You cannot clone this and make multiple copies and have the reference counter go up if the data cannot be written because you need to increment the reference counter. Okay, so we're gonna call it arc, and it's arc, and then we're gonna in the RW. Boom. Ah, look at this. This is like Rust soup, isn't it? This particular thing is a bit crazy. This is what we have now. So now we added another layer to this. So to get the list out, we have to ask the arc for this to get this, and then yeah, so it becomes even heavier to get it out, and we will do that in a moment. So this kind of thing strikes me as not very pretty to look at, and this has a lot of complexity. You could construct this in a single line as well, but here we actually, in order to have this safe structure, we're now doing 3 different steps implementing this. But maybe that is like the price you have to pay in order to have this speed and this memory safety. The other thing you could do here is that you can wrap this in another object or another structure if you want to simplify this construction process and getting this data out of it. It is possible to create this. If you do this frequently, you can make an abstraction, a form of an object that makes this go. Okay, let's continue. So now we have this arc here. The thing you can do with the arc, like I said, is that you can clone it. When you clone the arc, you get a value. It increments the reference counter by 1, and you get a clone that you can use. So that's exactly what we are now going to do. So inside our thread spawning, each iteration we're now going to make ourselves a clone that we move into the thread. Does that have to be mutable? Try it out. Let's try to make one. We're going to make the thread arc, so we're going to call it tarc. Tarc. And the tarc is going to be the arc, but clone. So now this thing here will have the same. Okay, was never used yet. There was an error message there. Let's tidy this up a little bit. Okay, so for each iteration of the loop, we are now taking now creating this one, and then we are putting it inside. This list is no longer valid. We cannot, so we cannot push to the list, right? What we got to do now is we can move the targ in here, and then actually what we're going to do is we're going to say, well, when the thread runs, we want to get this variable list, which is a mutable version of the list that came out of the RV log. Let's do that. Let list, so now we're redefining the list inside here, equals arc dot, yeah, so arc, no, actually it's not arc, it's targ. Okay, this is not very pretty. I'm gonna rename this thread arc, arc. Okay, so we're now going to say that what we want to do is we want to write with the RV lock. Look at this mess. It's just crazy. Make the text smaller to make this line. Well, of course, the reason we're seeing this is because we're actually seeing the types here in CLion. Okay, so we want our clone, we want the writable one. And then we don't know if that succeeds, but we're going to assume so. So we're gonna do expect. And we're gonna say the error message will be could not write. Okay. Now list will be an write lock write guard for this vector string. That means that we can hopefully use it. Okay, so it says cannot borrow immutable, right? Because list will be that. Okay, let's, I think we need to do something down here again as well. So we're just going to comment that out for now and see if we can run this and see. No, it ran. It compiled and ran. It actually tells us that the RV lock does not have to be, and neither, interesting. It tells us that the arc and the RV lock and the list does not have to be. But does it run? Does it allow me to compile that if I remove the mutability from these variables? Yeah, it runs. That is very, very interesting. Actually, it's super interesting because think about what we did now. We took this list, but we claimed that it is unmutable. Then we put it into the RV lock and then we made it mutable. But I guess there is nothing inherent about the vector. Nothing changes about the vector if it's or not. We just took our immutable variable and put it inside a system that made it eternally mutable. So maybe that makes sense. Yeah. Okay, so now we have to do the same thing down here. We have to unpack it, so we're going to do that. So now we're going to redefine, and we're going to say let list equals, and then here we're also going to, now we're going to do the same thing. We're going to take our arc, and then we're going to take now we only need to read, so we're going to read, and we're going to expect. The error message there is going to be could not get read lock, called read lock, could not get. And now we should have our list back from the RV lock. Just make this a little bit shorter. Okay, so now each thread writes their own number into the RV lock and now into the list. So what happens when it comes out here is that this lock guard should fall off the edge. It will drop because it is no longer used. And that means that the lock is released. So the next thread that gets to this point should then be able to acquire the write lock. All the other threads wait here while the first one that gets to this point will complete. And then when all the threads are done, then it continues down. We synchronize our threads. We come down here and we request a read lock and it should go. And indeed, it seems to have worked. We will also, we're going to add a new line here. So readable. No, actually, we're going to add a new line at let's actually separate them. And there you go. Again, it is interesting here that the order of the threads seem to be less chaotic now. than it was before. It might just, I think that when we ran this, when we just printed the eye, then it was a bit different. But that's not what we're doing now. We're actually mutating inside the threads. So we know that this principally now works. And then we do it at the end. Okay, so that was a lot of code for a small thing, right? This is one of those things that, of course, Rust, if you want to do something that is slightly involves sort of this kind of memory management and this kind of synchronization, you need to start looking at ARC, RC, refcell, cell, RBlock, mutex, and these structures that provide you these guarantees for how the memory will be managed at runtime. If you cannot use just these primitive Rust structures to do what you're trying to do. So I think, yeah, but I think we succeeded here in doing this. So what I will do now is that I will take a small break and then I will continue and try to use this knowledge to write that multi-threaded epidemiology model, but that is probably something that will take multiple streams because I see just writing this little set of code here took such a long time. So yeah, it is an extensive thing. Let's try to find. Actually, one thing I want to do before I take my break is I just want to show this code as it is without all annotation that CLion adds to. So it is much cleaner when you look at it without those annotations, but of course the annotations here with the types really help clarify to you. So Sea Lion is pretty good, I gotta say. And one of the reasons I'm doing this on Ubuntu here is that actually that the debugging is better in Linux for Rust Sea Lion. And just before we go, we can try to stop it here and have a look at the debugger. So the debugger in Sea Lion is kind of neat. It's like any other debugger. You can look into vectors like this and structures. So it's really good. I've really come to like this in C line. It's actually not a Rust IDE. It is a system for C programming, but there's a plugin for Rust that brains have made. Okay, so let's do a little break and then we get back to our epidemiology. Okay, someone drops in here while I'm away. I'm gonna make a new slide. It says that I'm back. Actually, I've learned about Rust. We can. I learned a little bit of Rust. Should add a check mark. A little bit of Rust. We have learned how to share data between threads, and then the next thing is perhaps more interesting, and that is to build an epidemiological model. Back. Next. Okay, short break. I'll be back in a second. Okay. And I'm back. Okay, so let's move on to a more interesting thing, perhaps. And this is to actually try and build something with Rust. I experimented a little bit with this over the weekend, and I thought it was an interesting sort of scenario for learning a bit of Rust. And part of the reason is simply that it should provide a lot of speed to do these kind of simulations. So the thing I'm going to try to make is a very, very basic epidemiological model that explains the development of epidemics in the sense that it shows you how the fact that people build up immunity over time makes transmission of the disease, successful transmission of the disease, less likely. And one of the interesting parts about these models, I think, is that they end up showing why not everyone gets the disease. And of course, you can play with the parameters in these models and see how they go. We're not really going to be doing anything interesting or groundbreaking here. We're going to do something that has been done countless times before, which is to just model infections and try to see the numbers at the end and how our model plays out. This might take more than one stream. I think I might also fumble along the way, since part of this process is to learn Rust. So it might very, very well be that we end up with something that I cannot, a problem I cannot fix, or and so on. So yeah. In the previous segment, of course, we showed that it was fairly easy, but on the other hand, also very convoluted to share data between threads in Rust. But we do show that it works with the RV lock and the arc objects, and that you can sort of bypass the limitations of the very, very strict borrow checker in Rust by using these structures to create sort of your own ad hoc memory management system that comes with safety guarantees. That's how I understand it at this point in my learning curve. Okay, so let's continue this. Um, let's drop back into Sea Lion. And this is where we left the project off. Of course, this was just to demonstrate the threading. So we will now go and we will create ourselves a new project for the epidemiology model and start that from scratch. So again, we load up cargo, which is the management system for Rust, which is both a build system and package manager. And people that know the language well praise this system, and I have no opinions about it yet. It seems simple and easy, and it imports packages from Git easily from GitHub, which is sort of all I need to know. Cargo new, and we're gonna call what we're gonna call this FBA model. Yeah. Okay. So now we have a new folder here called epimodel with the toml file, which is the definition of the package, and it also contains the dependencies, which will be taken care of. We also have our let's see, yes, also have our main file, and we will now open this project in Sea Lion again. So because I do like integrated development environments. I like Vim as well, but it requires more than I have. Okay. This is going to be a slightly larger project, so we probably have to modularize it. But what I think I'll do is that I'll start writing all the things more organically. I'll start in the main file, and then I'll branch out into different modules as I see the need for it. It should, coming from the C C++ C# world, it is a tendency for me that I always want to put everything in a class in a file. Of course, this is not really an object-oriented language, so sometimes it requires you to think a little bit differently. But I think we will we will gradually grow these modules, and I think we'll have each data structure and their associated implementations, which is effectively the same as classes here in Rust. We'll put those together in files, so it becomes sort of the same sort of one class, one file system here as well to organize our data. We can start with that. Okay, so we're going to start by Getting rid of this. And then we are going to create a structure for the simulation. So basically, we want to have a simulation. It should have certain parameters, and that simulation will then generate a virtual population. And then that population, we will seed some infected people. And those infected people will go on in multiple iterations and will have the granularity at 1 day per iteration. And then after 300 iterations, you will see how the infection has spread and then stabilized. And that's the idea of making one of these models. So we need to generate an ample amount of people. We'll start with something simple. We'll start with maybe 10,000 people in the simulation. Our goal is to get up to several million and keep the simulation running fast using multi-threading. Of course, does it really matter if you have 100,000 or 100 million people in your simulation? I don't know. I think presumably the dynamics are similar, but it might be that there are, if you make more complex models, that you want to that you need to include larger amounts of people in your simulation for it to be realistic. Like if you create clusters in your data set of where people live and how they relate to one another, then perhaps you need something bigger, more people in your simulation, but that's not what we're doing. We're making something much simpler here for the sake of this. The sake of this is not to do epidemiology, but to learn Rust, right? Okay, so let's continue this. So the basic sort of data structure in Rust, which also replaces sort of classes, is structs. So we're going to create a struct and we're going to create one for the simulation. So what do we put inside the simulation? We put, so I think I also want to have a structure which is called settings. Actually, let's keep it simpler now. We will just say, so we want the simulation to have a certain amount of people. So we need a struct for a person as well. I'm gonna call it person, individual. Yeah, let's create person. Something tells me these will go in different modules shortly. Simulation will contain a large amount of persons. So we will create a people variable that will be a vector of person. So the thing is that this particular object probably needs to be shared between the threads, or maybe we need to share the entire simulation between threads. But that adds some complexity because the simulation sorry, my headphones keep dropping out. So that adds some complexity because we want to share this data in a safe, memory safe way between the threads. So we will try to, we can try it without threading first, just to see that the principle works, and then we can branch it into threading and convert it into a multi-threaded system eventually. Okay, so we now have a vector of person, and of course for the simulation we will now create a factory method that creates it. So we will implement simulation. And the factory method typically in Rust is called new. So we will do a public function, public fn new. It will return a self. Yep. So we will do a simulation. The last thing that gets defined in a Rust function without a semicolon at the end, it will be the return what is returned from what is returned from the function, which is an interesting approach. It does certainly clean things up. Okay, so the people will be a vector and it will be empty initially. We don't want actually when we create a new one, maybe we here want to define how many people to add. So we will do that. We will say n, and we want that to be maybe an I64. We're never going to put that many people. No, let's I32. So we have a certain number of people, and then if we do that, we want to tell the vector. We don't want, so this is a dynamic structure that grows. So we want to create a vector with a specific capacity, and that capacity is U size. Okay, can we just do n? No. At a safe cost to U size. Okay, that's easy. The capacity, okay, so maybe can we just take this pointer sized unsigned integer type? Yeah, of course that is true. We will never want to have less than 0 people in our simulation. We just do that because that is the limiting factor. We do it like this, and then we don't need to do the cost either, and we have to worry about this when we generate it. Okay, so let's try to generate this structure. So let's sim equals, and this will probably have to be mutable. Keep that off for now. So the simulation is then simulation, and the size, let's start with 10,000 people, and then we have simulation. Let's see if this compiles. It does indeed compile with some warnings. So again, we're going to put this on the right. Go. And make this a little bigger. Of course, we're not actually using anything, so we get these compiler warnings, which is fine. Okay, so the next thing we need is that these people, okay, so the simulation needs to know, I guess, how many days. Did it need to know how many days it has been going on? Well, it certainly needs to run. So this is not an object-oriented language. Do I want a function that runs the simulation, or does the simulation encapsulate this behavior? So I think I feel like we need to have a run function inside the simulation. So we're going to create a public function called next day. Does it return anything? No. But it takes the simulation as a self, and since it's mutating, it has to be a mutatable version of self. This is a way of saying that this function, I guess this is a way of saying that this function can only be executed if the variable that you call it on is a mutable version of self, the mutable version of the simulation. If you borrow to a function the simulation, then the simulation cannot call this function because this one requires a mutable um, a mutable um, a mutable variable. So it has to be able to write to that. There are apparently limitations for when you can do that, when you can write. Like you cannot have uh, two mutable variables, for instance. That this is one of the things, or two mutable copies of a variable borrowed. Because then those two could fight over what version or they could fight over updating the object, and you have race conditions. Okay, so what happens during next day is, of course, we iterate the simulation. So we take some of the people that are infected will then infect other people. This tells us that the person needs to have status as infected or not. So what they typically do in these simulations is that they have 3 states. They have susceptible, infected, and recovered. So what we will do is we will do susceptible, infected, recovered, and dead. Although we would probably not need to have the last state, but we could. So our file is getting a bit messy now. Shortly we will split this into modules. So we're going to create one of these beautiful enums that Rust have, and this will be the condition state, person state. Yeah, we'll just call it state. You can be susceptible to an infection. You can be sick, be infected, you can be recovered, you can be dead. So we're going to simplify things a little bit here. We're going to keep the dead here because you want to count how many they are. You want to count how many people are infected at any given time in the simulation and how many people are susceptible. So that means that each person needs to have one of these states. A person will have state, so it will have a state, simply be state. Yeah, that is the basics. Okay, so in the simulation, we also want to have the reproduction number, which is how many people do you infect? How many people does each infected individual infect? So let's do that with the R naught. The R naught is going to be well, it can actually be an is it? No, yeah. So this one has to be a float, so we're going to call it 2. We don't need higher precision than that. Okay. Of course, since we added that now, we'd have to add it here to the simulation. I'm going to use a shortcut, add missing fields. So because, of course, we're thinking about COVID, we're going to say the reproduction number is 3. So each infected individual will, on average, infect 3 other people. On average. Okay. So now we need to think about practically how we do our simulation. So what we can do is we need it first of all to create these peoples. Now we have created the people is a vector with a certain capacity, but we want to fill this with n amount of people. So we need to do that. So we're going to make an implementation for a person. So that implementation will again include a factory to create it. So we're going to do, we need that. Maybe it's cleaner without. I feel sometimes that this is like constructors, right? Almost from we could, right now the person does not contain a lot of fields. So the constructor feels sort of arbitrary. The person only has a state. That state is always susceptible at the beginning because there's no immunity in our simulation. What we can do is we can simply create a lot of them here in the simulation function for now. We're going to take this vector out. We're going to say let people select mutable list of people, and we want that to be, and that is a vec with of person, and we want that to be an empty vector. No, we actually want that to be a vector with capacity of n. Because the reason for that is that when we create it with a certain capacity, then it allocates that memory up in front, and it doesn't. So sorry, I just saw a comment in the chat here from Jevon. I don't know what I expected. I don't know what you mean by that, Jevon. Did you expect this to be me playing video games again? Okay, so let's continue this. So this means that we now create a sufficiently large vector that we don't need to reallocate memory to the vector each time we add something to the vector, and that saves time in the initialization. Okay, so we're going to do for I equal I in 0 to n, so we want to repeat this. So now we're going to create 10, we're setting it up here. We're going to create n people, and here we say it's 10,000 people. So we're going to very rapidly create 10,000 people. Now we also get a chance to see how long that takes, and that is like instantaneous, right? Okay, so let's go at that. We're going to simply say We want the people push push a person, and the initial state for the person. Again, we're going to use the excellent autocomplete here for C-line, and we're going to say state is susceptible, actually. Still don't fully understand when I need to prefix it with this. If I just remove that, can I use it? No, I can't. Okay, state susceptible. Okay. We're now saying that we're now creating n number of people that are susceptible to disease. So that's basically what this line does. Let's try and run this now. Problems. Yep. So yeah, of course, we're not now we created that list, but we haven't moved it into the simulation. Of course, interesting. So like I said in the first part of the stream, there you go, it runs. First part of the stream, I said that when you don't borrow something by adding the ampersand in front, you give it away. You cannot use it after you simulation. Although we had some trouble with that in the threads, but here it does seem to work. Interesting. Initialization shorthand. This is also cool, right? So it will. So in Rust, you don't need to specify. Actually, that's also cool. So if we ask it to specify the R note here, which was float 32, and then up here, for instance, we then say that we want R note to be 3.0, should presumably it's this, right? There we are. Now we are creating. Yeah, so if you have a variable in the factory function here that has the same names as the fields of that struct, then we initialize it without doing any of the equal signs here, which of course simplify how this how constructing these structs work. It saves a lot of the boilerplate in constructors. That is good. So a comment in the chat, Jevin is thinking that I was giving Rust a go. Yeah, no, I haven't tried Rust. I'm actually learning this language for my project that I mentioned a couple of times, and I need to understand well how this program language works. And as you can see, probably it's still fumbling in the dark here, to some extent. Did you ever program, Jevin? Did you? Did you ever do some Python with bots or something on Discord? Okay, so we know now that when we run this, it does create those 10,000 people. We can try to squeeze the limit, so we're 100,000, 1 million, okay, 100,000, 1 million, let's get 1 million people. Actually, we also want to do the print line here at the end that says done. We're also gonna cache the whole thing. Line. We're gonna do creating sim. Okay, let's make sure we save before bots. And let's run it. Okay, that was very fast. Now we created 1 million people, right? Yeah, so it has. Okay, what about 10 million? Go slower. Still a lot of memory though that we did create there. What do you call it? System monitor. Let's see how much memory we are eating. What we can do is we can have a look at the resources here, and then we can debug it by stopping it at the last thing there, just to see how much memory we are taking from it. Okay, so this is the memory, and the swap is the memory right now. This is a virtual machine running at 8.3 gigs. Let's run our thing. We're going to debug it, so we stop it there. Let's see. And nothing changed. Why didn't we get? Is that actually? Maybe it quite simply didn't clear that memory. Sim, we now do have a very long vector here of person. They are susceptible. Single susceptible. It's good. Okay, so now how many was this? 10 million people? Should we go for 10 billion? Freeze. So now we are at like 10, 3. So now we are 100 million. Creating. Here my computer fan spins up. That was also really, really fast. It appears that these data structures did not require a lot of memory at all. We are still at a very low memory consumption here. Unless it optimizes it in some way. That could be. It could be that it sort of drops it immediately because it will be used. So we're gonna make sure that that optimization does not happen. And we're gonna say, I want to know, we want to know how many people are in here. So we're gonna do n equals, and then we're gonna go take the sim, and we're gonna take the people, and we're gonna take the length of that, so that we actually know that we have to use that variable. It could be that the compiler optimizes that out. If not, it's super awesome. Okay, creating sim, and it spins up. Hardly used any memory, so maybe these structures are tiny. Maybe that's just what they are. They just have one enum each. Yeah, that is of course something to think about. It's a very small memory structure. It takes a bit of resources here to create all those, but it consumes very little memory grand total. Okay, let's continue this. So what we have now is we have our simulation. We can create a simulation. We populated it, so we're gonna say create people, create simulates. Sims. We're gonna drop this down again a little bit because I know this is a bit heavier. So we're gonna put that out, and then so now we could think about moving this into another module, but let's keep it here for time being. So the person has a state. So now we need to have a mechanism. We need to run for n number of days. So we're gonna keep what we need to do every time it goes to the next day. Actually, let's do something else. We now want to seed a certain amount of sick people in our simulation. What we're gonna do is we're gonna go through this mutable sim, and we're gonna pick 10 random people, and then we are going to make those people infected. That means that in the next round they will infect further people. So that means that yeah, so now we have to make some decisions about whether we want the infect function to be a function of the person or the simulation. So I guess in Rust you have to think a little bit about this. It feels very natural for me. So if I was creating this in Python, I would say that each person contained a reference to the simulation. And then this of course creates complexities. So basically what happens in this very simple model is that if you infect a person, we'll get back some. You will over time, over a few more days, that person will trigger infections in other people, and then they will get sick and they will trigger infections in people too. I think what we're going to do is we are going to say that each person carries with it a sequence of days that they are sick. The disease lasts for a certain number of days. The infections of the other people are not instantaneous; they happen over some time. So we want once a person gets infected, you generate you generate a sequence of days or a course for that individual disease. And then every sick person, every infected person, every new day you pop one item off that sequence. You take the first item off that sequence. So the sequence gets shorter, and then the last item is the final state person. whether the person lived or died, or recovered, or passed away. Beyond that point, we're not interested in that person. We're only interested in ticking or changing the people that are infected. This also optimizes, I guess, how fast the simulation runs when there are few individuals, like at the beginning and the end. So I think we're going to implement that on the person. It feels more natural to do that. So we're going to implement person. And when a person gets sick, we need to have a function called, so we're going to have a public function called infect. So infect will generate a course for these individuals. That the person needs to have a course, a disease course, like how it runs. So because of that, we also need to add each day in that. Some of the days that person infects someone, and some other days it will not. That person will not infect someone. I think we're gonna. So we're gonna we create one of these beautiful Rust enums again that can contain data. Nice. This is a cool thing we can do in Rust. We can now create sick days effectively. Not like in a sick leave sick days, but we're going to create sick days. What I mean by sick days is that these are the things that can happen while the individual is sick. So it means that we will, or is that, yeah, that's the way to, yeah. So either or transmission, actually that's what we're going to do. We're going to create an enum called transmissions. Transmissions. And either you infect none, infect someone. So a transmission is either, it's going to be transmission. Either you don't infect anyone or you transfer it to someone, and or one or more individuals. So you could, for each given day, you can either that you are sick, you either give it to someone, or that could be multiple people, or you give it to none. So a transfer or an infection, how do we explain that? Yeah. I could just mention infects, we can call this, so it's infects. Then we're gonna have a list of numbers, which are the individuals that you infect in simulation. And the individuals, we're gonna keep this very, very simple. And we're gonna say, because we know that the list of people is ordered, so it will just be the index in that list of those individuals. If you wanted to make a more complex epidemiology model here, you would probably want to have clustering. So who you infected would be weighted against, so there would be small clusters of people that were somehow connected, and those people would have a higher risk of getting the infection from you. But at this point, we'll just pick some people from random from the simulation to make it simple. Okay, so we need a list here, so we're going to add a vector, and it was a usize, which was the variable type. So I create a vector of usize that represents the people you infect. We're actually going to do one more interesting thing here. We're going to create a type alias for usize, which is ID. Because it feels more natural now that we talk about an index or a person ID, right? So we're going to do type. How is the syntax for this? ID equals size. Yeah. So now these are the same thing. So, but it makes more sense. We could actually create this person ID, but I think ID is better, and ID just means the ID of that individual. We could also add the ID to the person here. Perhaps we'll do that. We're going to add ID, and then the person will be given the ID of the iteration that person is in. So the ID, and the initialization thing should work like that, right? So we're now saying that the same way we are now creating n number of people, so we want to create millions of people in our simulation, we're just giving them the ID, which is the number, and that's also their index in the list. So the first person is 0, the second is 1, and so on up to maybe 5 million if you wanted to simulate the entire country of Norway. Okay, so person again has a state, but now we're also saying that the person has a course. So once the person gets infected, the person is sick for a random number of days. It's not random, it's semi-random. We're going to pick it from a distribution. So we're going to say that the person is sick perhaps for 14 to 21 days. Of course, we're going to simplify this. Actually, we can simplify this. We can say that everyone is sick for 14 days. Then we don't need to worry about picking that number from our distribution. But if we wanted to have a variance in the thing, we could also use probably pick people from the normal distribution or something like that, or pick how many days they would be sick based on the distribution like that. But I think we'll just, for simplicity, to keep this simple, we're just gonna keep it at 14 days for each single individual. So a person will then have a disease course or development course. And what is course? Well, a course is a vector of sick days. Did you call it sick day? Oh, it's a vector. Okay. Yeah, we call it transmission. I think sick day was it nicer? I don't know. Yeah, it doesn't matter. It's bike shedding, isn't it? Of course, it's not just bike shedding because it means the readability of the code is better like this. So I'm gonna come here, gonna see what is well. Person has a course of sick days. Actually, here we could use an array in in Rust. Arrays, as far as I understand, are hard coded at actually they're hard coded at compile time. So you will not be able to use an array here because they will have presumably variable courses. I do want to keep the ability to tweak the R parameter because it could be interesting, but we could simplify the model further and say that people are sick for 14 days and they infect someone every 5 days. Well, that would also be the last ones. 4 days they would infect someone on day 1, day 6, and day 12. Then that would be an approximation that was good enough just for these tests. Again, we're not trying to do epidemiology here. We're trying to learn this programming language with all its intricacies. Okay, so when a person gets infected, we need to populate this course. We're going to say that when the simulate in the moment, we're going to say that we're only interested in people that are sick. So in this thing that ticks the simulation forward, so you want to run this function 300 times to simulate 300 days of 5 million people. So then I think when it gets infected, we're going to create this course vector and fill it with sick days. Let us keep it simple and say that when you get sick, you infect someone every 6 days. Make sense? And if you're sick for 14 days, you have to infect someone every 4 days. That makes more sense because then it's sorry, my headphones keep dropping out. So if you infect someone every 4 days, then you infect someone on the first, the fourth. Oh yeah, no, you infect someone on the fourth, the eighth, and the 12th day. That it's good enough. Like yeah, you could perfect this a lot more if you wanted the variance. The question is if the variance matters to us, and I actually don't think it does. We're now going to create a course, and the course the course is going to be static here. So we could, I think it's nicer not to hard code that particular course. Yeah, okay, but anyway, so we're going to take a person and we're going to infect it, and that means that the person needs to have a mutable reference to self to work. Now we are going to update our course, so we're going to create let course equals, that's going to be a vector of sick days. Actually, it has to be like this. It has to be, you have to declare a type. So course is a vector of sick days. Then you can create the vector directly like this. Made that. So how are we going to do that? So we're going to 3 times we're going to loop for 4 days. No, we want 40. Yeah, we can just actually do that. We can do for round for r equals 0 to 3, r in is the thing. R in 0 to 3, then we want actually each one of these 3 rounds we're gonna create. We're gonna add same structure to it, and that structure is gonna be gonna push into course. Course, can you do append back, and then we can it's sick. It's none. Oh, that's wrong. It's sick day. So we're gonna first day we're not gonna infect anyone. Then we're gonna not infect anyone on the next day. The next one we're not gonna infect anyone. Sick day, none. And then the final day we're gonna infect someone, and then we need to pick who that's gonna be. So we're gonna say infect. And of course, we added the opportunity to have multiple people sick. That you infect multiple people, but we're gonna simplify this further to keep it just within bounds. So we're gonna say that you infect the person with a given ID on that day. On that day you infect someone, and that's gonna be ID, and then who is that? Well, now we have to pick randomly who that's gonna be. Does this work? Has to be me. Yep. Does this work? I think that worked. So we are appending a vector, which is sick day, none, none. So we have 3 days where we don't infect someone. The final day you infect someone. Ask me, oh, that's not nice. Really, how that's gonna be? Does this work? I'm a bit concerned that we haven't compiled something for a long time, and that once we push compile, nothing is gonna work. But actually, we should probably build this now before we complete it. How that goes. We also, yeah, so we have to update here where we create the people. We have to create an empty vector for the course. We can remove breakpoint that we use to test the memory consumption, and then now we're gonna build it, see how that works. Yep, so it built. Sim and it's 10,000. Okay, good. So now we're gonna do this. Initially, we can just try to say that everyone infects person number 1 for person number 1. And then we're going to say that the course equals course. So let's see if this compiles. It compiles. So what we are going to do now is we're going to pick at random some people from our population, and we're going to do that 10 times, and we're going to make those people, we're going to infect those 10 people. So we're going to say for E in 0 to 10, we're going to choose a person from the distribution. So we're going to use sim people choose. Okay, so here's the thing. Rust doesn't come with built-in Rust does not come with built-in random number generators, so we actually need to add ourselves a random number generator. What we're going to do is we're going to go into the cargo file that has the dependencies, and we're simply going to write rand. So CLion will then look up the available packages, and we're going to choose rand. We're going to add rand. Now we've added this to our system. Yeah, so rand is a package for random number generation. And it has this function called rand, and we can use that. Okay, so let's take this. So now we're going to use, okay, so let's see how this works now. So I'm going to use rand. It's random. I think random just gives you a number, but it also has that choose thing, and that, I think that's the thing, because we can just then pick a person. We can also do random and multiply it by the, so we have up here, we're going to say n Yeah, so actually we can actually just multiply that by the number of people in the simulation, which is probably so we can do say let rand idx the index equals actually this is u so actually so rand of course gives you a floating point number, right? So it's going to be f30 64 64 equals random. Stop it here to see what that is. Now when I push compile, it imports those. It imports for you missing packages, which is cool. Because they didn't do anything because of course it's. So we're gonna do random, and then we're gonna. Oh, we're gonna do let idx. I think we can redefine the variables. So we're gonna take. Can we redefine variables? idx times. We want the sim dot expected f64. But that's fine. We can do f64 as it has a thing here that says can you save cost, right? So let's save cost. Because now we have the IDX. So this actually compiles. It compiles, so you can redefine variables. Okay, that's useful. So okay, so let's just stop it there to see this if this is like we expected. It's indeed a very high precision random number. What I want to do now is can I take this and can I cast this as a U size? I think I have to round it and then I can pick an individual. Let's try this. So let person, so actually we redefine this. This is, we can pick the person by saying, yes, now we have to do sim.people.get to be immutable, and then we're going to get this particular IDX. So let person equals. Indeed, we get an option, and we're just going to unwrap that because we have to sort of set it to get a mutable person. Let's try that to work. Files, and then we say person effect like that. Then that person should now be affected. So, just do line affected. Then we do this IDX here. I'm doing that because I think what I want to do is I want to give a reference to it, right? I have to. This is a copy type, right? That's the thing. So I'm not actually. Oh, maybe that's what happened to the I. So now it has infected random people here in the simulation. Let's just run it a couple of times in case there's like runtime stuff happening. Okay, so now we are infecting certain individuals, and I want to just stop it here and have a look at that individual and see that it does what we. The person now has a state. Okay, so the person is still susceptible. Yeah, because we didn't put infected. That we can do right away. We can go infect function. So we have defined a course. I mean, I say that the person. Of course, that is also a thing because you want the person's. Yeah. So you want the person's state on the final day of the disease should define whether that person lives or dies. Yeah, okay, so there are some interesting things here. So now we have two things that happens along the way. On one hand, the person is you have infected the person. Yeah, so now the person's new state state equals and then what was it called? Was it state? Yeah, so the person is now infected. So once you've infected the person, you've changed the state of that person. Let's try and run this. So we're looking now at the person, and the person is indeed infected because we picked a person at random and we have infected him. So now the person also has a course. These are the sick days, and on the fourth day, okay, so the third day, okay, so on the third day, the person infects someone. Right now, everyone infects person number one, of course. So I think what we'll say is that for each infected person, we take the first element of that list and remove it. And then, once the list has no more sick days, then we set the status of the person to be either recovered or dead. We could add that as the you could add that to the to the course as like a state of what happens that day. We could also add to that. We could add a lot of complexity to the course of the sick days. We could say that there's an incubation period, and then there is the infection period, and then there is the final element. It's the conclusion of how it happened, if the person was recovered or dead. For now, let's keep it simple. So that seems to work, but what we do want to do is pick a random person, and we do want to take. I think we do want to create a function that does this, because this is not very nice. So we're going to create a function that takes care of this. So we're going to add that to the simulation as a public function called pick a person or pick person, pick random. So what do we need? Well, we need a mutable. We don't need a mutable reference to self. We need unself. We just need to borrow self. Then we'll set self that people get muted. Okay, yeah. So of course it has to. This probably means that we have to. Yeah. So self has to be muted. Yeah. Okay. This has to return a unmuted person. Is this going to work? I don't know if this is going to work. So we know. I'm just wondering if this will function or if this is a problem for the borrow checker. That. Yeah, so here's actually, I forgot to remove this, and then this doesn't become a return statement. This is a mess. Yeah, so that. Okay, so that also compiles. So let's try this now. I seem to have some distrust in the Rust compiler actually doing its thing. So let's now replace this. When we where did we do that? Here we do that. So we're now gonna say we're gonna remove this. We're gonna take the person. And here's the question: is this gonna work now? We're gonna say let person equals sim.pickrandom. Can we do this? Are we allowed to do this? Are we allowed to take this mutable reference out of the reference to the sim? No. Okay. Why? What happened there? Yeah, of course, this thing is not scope. Actually, what we can do is we can do person.id, right? Because we took that out. Yeah, so that also worked. Okay, so you can take that mutable, simulation, and you can get a mutable, you can borrow a mutable individual from that vector and take that out. So that also works. So far, Rust has not really provided us with any of these huge fights with the borrow checker that we are concerned about, right? So far, we only get the beautiful type system to work with. So that is kind of cool. Right, so let's continue our journey here. We can now remove all this dirty coding here. We have a function now to pick a random person from the simulation. So we will do the same. Yeah, of course, now we're talking, right? Because, okay, so in the person function, we have to pick a random person. So what we want to do is we want to infect an individual here. When the person gets infected, the last thing here will include the ID of a person that gets infected. So we're gonna, but of course the person doesn't know the simulation that they are in. So now the question becomes, can we then provide a mutable reference to the sim? We're going to create a variable called sim, which is a mutable simulation reference. And then we're going to pass that on and try to get that individual. So let person equals sim.pick random. And then this works. We will take the person.id. Oops. There. Okay, so we can say person.id. I think this works because it's a copy type. Okay, is this gonna work? No. Okay, yep, so we have to provide with more arguments. So in main we're infecting, and then let's see if we can pass and pass sim as a mutable into there. Cannot that. Okay, so here it stops. Second mutable borrow occurs here. First mutable borrow occurs when we pick a random person. Yep. And then we get a mutable person back, and then we cannot. So we can, yeah. So okay. So what's the thing there? Yeah. So this is the borrow checker thing, right? Let's try this. So we are picking around. We're taking the mutable position. Then we are. Yes, let's say that we remove these. So the only thing that happens here when we're creating it is that we pick a random person. So that worked. So then we have a mutable person that we have returned. The problem comes here now. Why is that? So now we're sitting here and we have a reference to a person inside the simulation, which is a mutable sim. Is it because we now have this person we cannot do this? What happens if we drop person here and then we try and do it? Borrow a value person. Yeah, so we're not allowed to do this quite simply. I think what we're going to do is we're simply going to, instead of returning an actual person here, we're going to pick random, return the index. We're going to return a usize. We're going to change this and we're going to change that into, let's see. We're going to rename that into pick random index. And then we are going to return the index from there like this. And then, because then this is a copy type, so we're not borrowing this, so we're passing that out and passing it back. So let's try this again. When we are populating here, we are not actually out. So now change this into EX. EX. Person infect. It's because there is yeah. And then we are going to, yeah, so we have to find the person. So to do that, we do sim.people.get mutable, and then we're going to do idx and wrap. Actually, I'm getting this night shift thing. Night light. That's what it's called. Helps me a little bit with the colors. Okay. So let's continue this. Okay, so now we are getting the index of a random person in the simulation. And then we are getting the person. So we are, let's person. Then we're getting a mutable person from the simulation like this. And then we have to go to this function. We're going to this reference to the simulation. Can we pass that in now that it's not the same way? Let's have a look at it. So we're going to try to run this, let's see, simulation infect. So we're going to infect just for now. We're just going to see if we can get the person up now. So actually, I doesn't have it's IDX that we're using. Oh yeah. Okay, so it's see this run now. So now it runs. So now we are picking people, and we can also get the okay, so we can also get the person as mutable out because we are now just getting the index, and now the question is, can we infect the person and pass the sim into it? So we're gonna borrow mutable the sim. Borrow mutable more than once. What if we only borrow the sim? Does that work? Because what we need is we just need the ID of that person, so we don't need to actually borrow it mutable. Doesn't work. Well, borrow occurs here. Yeah. Because it's actually getting quite late as well, so I do think that maybe I will have to continue this stream at a later point, like I said. I think what we are looking at here can be fixed. The simplest way to fix this is simply to say that we are picking just a number from this list, and then we are choosing the person from that. Because the problem right now here, it seems to be that we are borrowing simulation to infect the infect method because we need to get that number. So we could just provide it with a victim here. I think that's simply going to work. So right now we're simply going to ask the simulation to pick a random one more time. And then here we're going to do, say here's the thing again, we would need to have 3 of these, right? Um, this is a little bit of just a little bit of a pickle here, how to structure this, right? Or how to think about it. So, because some of these things that you would normally do in other languages would be fairly simple, right? But now we are sort of stuck at this, although we could still do this simply by saying the maximum size or number of people, or the size of people, the number of people in the list. We could just feed that into this function and pick a number within that range. That seems messy, right? You want somehow be able to read that out. So what the way that I would perhaps normally resolve this would be that the person object also carries a reference to simulation. We could do that. That required a reference counter, I guess. It had a RC or arc like we did in the first part of the stream, so that each person would have a reference to the sim. But you cannot. Yeah, and then you would have a RV lock inside that arc, so you would have the same kind of structure, and then you could read or write from the sim as you wanted to, and it would provide that multitasking ability that we're looking for here. Yeah, these are the pickles that you get into with Rust. You have to the argument everyone says is that you should not fight the borrow checker. You should do what it wants. The question is what it wants. Cannot borrow sim as immutable because it's. Does that mean that I borrowed it someone before? That's what I did here. Is it still borrowed? Yeah. Okay, I'm going to think a little bit about this, and I also need to eat something. It has been a long stream, but I hope it's been interesting if anyone's interested, and then I will certainly make a second part of this, maybe not tomorrow, soon, where I will have a look at it again and see if I can solve this. I also need to read up a little bit to figure out what is the best course of action for this. But it is these are the things. This is exactly, for me at least, this is exactly what the learning curve is. This like I understand the syntax and how it works, but the way you structure data is different, right? You cannot use the same methods as you've become accustomed to. So these are the challenges. And actually, one thing that I do miss in Rust is that is to have in the learning curve or in the material that's available to learn Rust, that there existed sort of tutorials for how to solve these problems. Like the same way that you have when you learn Kotlin, you have the Kotlin koans, which contain these puzzles that you have to solve. And in a way, I wish Rust had these kind of koans that you can go through for complex things like data structures, like design a non-directional graph, design a linked list. Yeah. Okay, I think that's it for now. If you have any comments, please leave them, and I will be back later to try and crack this nut here. Okay, I hope it was useful or interesting to whoever watched, and I'll see you again in the future.